so far we have been discussing some portion of queuing theory. Now we have come to the critical juncture of discussing the actual queuing process. So we have already talked about two things, one is discrete time Markov chain and continuous time Markov chain. So today we will start discussing about discrete time Markov chain. So that was the discussion of the last this one. So we will start our discussion of this DTMC. Let us try to understand some of the properties of these things. So for that, let me give one example. Let us say just a system I am trying to create. Let us say there is a random traveler who actually goes from city to city. Okay, so I am just taking one example. You can find this example also in the book of Kleinrock. So basically, let us call that city 1, 2, 3. We can take any city name. So it might be Delhi, Calcutta, Bombay, something like that. Okay. So he is moving around from this city to this other cities. Okay. Now how he does that? So there are some assumption to this. Of course, it's a hypothetical thing. So we'll be taking some example or some assumption to that example. So that's what we are saying, that it's a hypothetical example, and he might be in a particular. So every day, if I see the time is slotted because it's a DTMC. So time is slotted. So let's say every day at let's say 8 a.m. or 8 p.m. let's say 8 p.m. in the evening, he catches a bus, okay, to move to another city, but which bus he will be getting, that's random. So we beforehand he also doesn't know, and beforehand even the observer also doesn't know. So he can catch any bus, but with some associated randomness. Okay. So basically, and from there immediately he will be, and this transition from one city to another city, so that bus is almost like teleportation. Okay. So it transits him immediately. Okay. So immediately he goes to other city according to whatever probability he takes of some bus he catches. He might be in city 2 on a particular day t. So he might be in city 2, and then 8 p.m. he might catch any bus for city 1 with some probability, any bus for city 3 with some other probability, or he might remain over there. Okay. So that might happen. So of course something will be happening. So therefore his probability of transiting to city 1 or city 3 or city 2, overall sum of that will always be 1. Okay. So that is something you have to keep in mind. So whichever city he is there, so his probability to transit to other cities, those probability, if you sum overall possibility, that must be 1, because that should be, he must be doing something. He must be either going to some other city or he will remain in that same city. Okay. He cannot do anything else. So therefore those overall sum of those probabilities should be 1. Now these probability, what are those things? So every time, every 8 p.m. of every day, he actually inserts those probability. So these are called actually the transition probability from one city to another city. So therefore on day t, we might have some probability, for, suppose I have observed him in city 2 on day t, and then on that day he is transiting. So basically he might have some probability to transit to some other city, and what's that associated probability? So those probability will be characterized by the transition probability given by the description. So there might be some transition probability p to 1, there might be some transition probability p to 3, and there might be some transition probability to himself p to 2. But whatever happens, this p to 1 plus p to 2 plus p to 3 must be equals to 1. This must be happening, and this is true for every city. This city also same thing will be happening. So there is a transition probability P12, there is a transition probability P13, and there is a transition probability to himself P11. Again same thing will be happening. So P11, P12, P13, must be equal to 1. Similarly, for 3 also same thing. So, he might transit over here, he might transit over here, or he might remain over here. So, this will be P31, P32, and this is P33. So, again P31 plus P32 plus P33 must be equal to 1. Okay. And if you see, I can represent this. So, basically what you can see over here, these cities where he is, that makes the state. Okay. That is actually making the state. So, those cities are the state where he will be, where I observe him. So, any day I try to see, I will be describing by where that particular traveler is located. He might be in city, because that is a random thing. He might be in city 1, city 2, city 3. If I can describe that where he is, that should be the description of, means description I wish to make, I wish to inform. So, because of that I describe that as to be state. So, he might be there in state 1, 2 or 3. So, that is the overall state space, okay, because we have considered 3 cities. If we consider 5 cities, then the state space will be 5, and he has a possibility of being in every city. Now, this is probably random, because which city he will be, that completely depends on where he has started and how he is transiting. Okay, with all probabilities it is happening. So, therefore, which city he will be, that is also probabilistic, because it is a random process, right. And so, therefore, there are states, and associated between state there are transition probability. And if you see, if there are 3 state, I can have a associated transition probability matrix. Okay. So, which is this one, P11, P12, P13, P21, P22, P23, P31, P32, P33. Of course, their summation, the row summation should be all 1. This typical matrix where the values are all probability, therefore, they lies, all these Pij's are always between 0 to 1, their row sum is always 1. This typical matrix, which is actually a transition matrix for capturing the transition probabilities from one state to another state, or all possible state to all possible state. So, this is termed as Markov matrix. Okay. So, Markov matrix has this nice property that they are generally probability value and their row sum is always 1. Okay. So, that property is there. There are additional property that probably we will not be requiring. Okay. If we do a full fledged queuing theory course, probably that thing will be exploding, but right now probably this is good enough for us. Now, let us talk about this state and transition, these two probability things we have got from this description. Okay. We have now understood what is a discrete time process. Of course, it is only happening at some time, means boundary, it is not happening anytime, it cannot happen in between anywhere. Okay. So, the way we have described the system, it can only happen at some particular boundary. So, okay. So, it can only happen in some particular time boundary only. So, therefore, it is a discrete time process. I know the state transition are happening only on that boundary, on that specialized boundaries only. It cannot take place at any time. So, that is why it is a discrete time process, and it has an associated probability of transition from one state to another state. So, basically it has a state description, which state it can take. Over here, as we have told, that we will be concerned about discrete state only. So, over here the example also we have taken as discrete state. In our queuing, it will be just number of customers. Okay. So, it might be 1, 2, 3, something like that, or even 0. So, it will be just transiting from that. So, from 0 it will go to 1, like in our bookkeeping we have already seen. In queuing, what might happen, it can go, the queue length might increase from 0, it can go to 1, then 1 to 2, again it can come down 2 to 1, something like that. So, all those transitions, associated probability we are now talking about over here. And of course, remember it is a discrete time process. Earlier whatever bookkeeping we were doing, that was all for continuous time, but right now we are concerned about a discrete time process. Okay. So, that is our whole description of the system. Now, let us try to see what can we say about these two things, state and transition. So, first we will start with transition. Now, the transition, what might happen there is no restriction. So, every day there might be different probabilities that he takes. So, that means this transition probability itself evolves over time. This might happen that on day 1 probably he was having some other probability, it depends on his interest, it depends on the associated bus availability and their arrival randomness and all those things. If those randomness changes over time, then probably different day there will be different probability of him going to another city, from that city to another city. That means the transition probability will be varying over time. If that happens, then it is called a heterogeneous Markov chain. Of course, I should put heterogeneous Markov chain. Okay. If the transition probability, which will be more of our interest, that generally the transition probabilities does not, the system description does not really change over time, the kind of system we will be taking. Okay. If that is the case, then that particular kind of Markov, associated Markov chain or associated Markov process is called homogeneous Markov process or associated homogeneous Markov chain. We still have not talked about what is Markov chain, but we will come to that in due course. Okay. So, we will be mostly interested in this homogeneous Markov process. So, therefore, this transition probability will not be really varying over time. Okay. If the transition probability is not varying over time, can you now say the associated state probabilities, will that be varying over time? Let us try to inquire that. Okay. So, that is exactly what we will be now next doing. Let us try to this part. Okay. So, what we have told, that let us have that particular random traveler example. So, we have state 1, 2, 3. Let us say associated probabilities we put with pi. So, pi 1, pi 2, pi 3. Initially, we will think that they are varying with time. Okay. So, basically we can say pi 1 time is now discrete. So, I will give pi 1 n, pi 2 n, pi 3 n. So, in the nth time instance, because it is a discrete time. So, time instance 1, 2 like this it goes 3 up to n. So, in some arbitrary nth time instance, these are the state probability. Okay. Let us try to see how do I characterize the state. So, right now what we have taken is a homogeneous Markov chain. That means, my transition probability matrix, which is the P matrix, which is consisted of this P 1 1, P 1 2 and so on. So, all these things are not varying over time. If it was heterogeneous, then I just had to write P n. That means, in time instance n, what is the associated transition probability. If it is homogeneous, then P n's are all, for all n they are equal. So, P n is equal to P n minus 1 is equal to, so everybody is equal, because the transition probability matrix is not varying. Now, how do I get a relationship between the transition probability and this one? Can we now try to characterize that? So, let us try to understand these things from the probability perspective, basic probability perspective. So, let us say on day n minus 1, he has an associated probability pi n minus 1 that he is in city 1, pi 2 n minus 1 that he is in city 2, and pi 3 n minus 1 that he is in city 3. This is the associated probability. Now, what is the probability of finding him in the next day in city 2? Let us say I want to calculate pi 2 n. Let us try to see how do I evaluate this. So, the evaluation is very easy, that in the previous day where he was and associated transition you multiply, because it is a where he was, that is independent of what transition probability he will be taking. So, these two events are independent, so I can multiply them. Okay. So, therefore, suppose he was in city 2, pi 2 n minus 1, and then if on the next day he has to be in city 2, then it has to take a transition P2 to from the same city 2 to himself, he has to take a transition. So, therefore, this is the probability that if he was in city 2, if I multiply with P22, then he will remain in the next day city 2. So, that is the associated probability, but is that all? No. He might also be in city 2 where in the previous day he was in other cities, and those events are mutually exclusive. Okay. So, therefore, that probability will be added. So, pi 1 n minus 1. So, he was in city 1 and then he does a transition 1 to 2 plus pi 3 n minus 1 and then he does a transition 3 to 2. Okay. That is the associated thing. If you carefully see, I can like that, I can also calculate pi 1 n and I can also calculate pi 3 n. If you carefully see, this is just a matrix multiplication of a associated vector. If I just construct a associated vector which is actually pi 1, pi 2, pi 3 with time index, let us say n minus 1 if I put, then it is a overall pi n minus 1. Okay. So, that vector, if I put pi n, then this will be index will be n. So, if you carefully see, it is just associated this vector multiplied by this transition probability matrix. So, basically pi n minus 1 vector multiplied by this p vector, that must give me my pi n. This relationship in a very simple way is always true. Now, of course, if the state variable becomes having more value, then definitely the transition matrix also will have means matching values, and this multiplication, this vector to vector and matrix multiplication will always match dimension, and I will accordingly get how many equation I get, as many number of variables are there, that many equations I will be getting. So, this gives me the number of equation. If I know the transition matrix, if I know the previous time these values, then I can always calculate from there the next time what will be the value. So, basically the state probability evolution I will be able to capture from the previous one. So, if I know at 0 where is that, means if I say okay, I drop him in city 1, then the associated pi matrix pi 0 will be, so I have dropped him in city 1, others will be 0, and from there with the transition probability matrix I will be able to capture what will be the associated probability in second day, and then from second day again I can capture what will be the associated probability in the next day, and so on. This I will be able to capture. Now, even if the transition probability matrix is P, okay, which is homogeneous, I have no guarantee that over time this probability will not be keep on varying. Okay. If I have an additional condition that P is means such a matrix that this to this transition they gets actually a stationary value. What does that means? That means if I go up to time infinity, then I will see that actually wherever in the initial condition or whatever initial condition I put, or wherever I drop that random traveler at 0th day, enough time if I go, then the probability associated state probabilities will become convergent. That means it will take similar kind of value. If this happens, then that particular random associated random process or the Markov chain called is termed as stationary Markov chain. Okay. Not only stationary, in time also if it is getting similar thing over time, then we also call that it is probably ergodic Markov chain. We will not go into the details of those description because that requires a full again a full fledged queuing theory course, but right now we can just understand this property that if this happens, that means this not only the transition probability, but the state probabilities also are not varying, they are being constant over time. Okay. So, what does that means? If I put limit n tends to infinity, then this pi n minus 1 or even pi n, these are all going towards a stationary value of pi. Okay. So, immediately what I can do in this equation, I can take that limit. So, if I take limit n tends to infinity in the left hand side, and if I take limit n tends to infinity in the right hand side. So, basically both of them will go to pi and p does not depend on n. So, therefore, I will get a equation which is called pi equal to pi p. This is famous stationary discrete time Markov chain queuing equation. You know what has happened? Now, I have got, see, the state probability, if you do not know about them. So, if I just write this equation, that newly derived equation, pi equals to pi p, what is this equation actually? So, if you see, it is actually set of linear equation of pi. Pi is my unknown, the state probabilities I do not know, I want to solve them. So, basically I get a state probability associated equation. How many equations we get? We actually get, if there are in the state, suppose in our that random travelers experiment we had 3 things. So, I will be getting 3 equations involving 3 variables, pi 1, pi 2 and pi 3. So, I will get 3 equations from here. Now, from this 3 equations there are 3 variables, will not be able to completely solve it because we do not have any constant things. So, we will get a non-trivial these things. At max what we can get an interrelationship, pi 1 to pi 2, pi 1 to pi 3. So, this relationship, we need another equation to solve the whole thing. So, that extra equation will be, we also know that Hippie must be found somewhere. So, this summation pi I is equals to 1 over all I. So, this last equation will get interrelationship from this particular matrix equation, will be getting interrelationship between each of them, pi 1 to pi 2 and pi 3, and then this normalization, because all this pi summation should be 1 because it is probability. So, their summation should be 1, I must be able to find that particular random traveler somewhere. So, that summation will be 1. So, just by doing this we will be able to solve the whole Markov process. So, basically a discrete time Markov chain, what now we have understood, it means as long as we take 2 assumptions, one is the homogeneous assumption and the second one is the stationarity assumption. So, basically the transition probability matrix is not changing over time, and then the last thing what we have discussed, the stationarity, okay, or the stabilizability. So, that also is taken to be true. That means, if I go observe the system for time tends to infinity, then the state probability also do not change over time. It has some probability and it stabilizes to that. Okay. So, it is stationary. So, if we take homogeneity and stationarity assumption, that will be taking, there are some conditions we will right now probably we will not discuss, later on we can discuss them. So, with what condition they happens, we will discuss that later on. But if these 2 things happens, and in our system it is guaranteed that these 2 things will be happening. So, then we can describe the whole system. We are interested in solving the state probability, that for a queuing, how many times I found the queue, or what is the probability, associated probability that I found the system without any customers. So, that means in 0 state, with 1 customer, that is in 1 state, 2 customer, that is in 2 states. So, all these associated probability I need to find out. Okay. So, these probabilities, if I wish to find out, I get a set of, from this particular equation set, I get a set of linear equation. So, all I have to do is, along with that I will have this normalization equation. So, I solve this linear set of equation and I solve the state probabilities. So, it is as simple as that. So, therefore, means if I can guarantee that these 2 conditions are satisfied, homogeneity and stationarity or ergodicity also for the time being, if these 2 are satisfied, we will be able to characterize the system by set of linear equation. As many states are there, that many set of linear equations will be formed. We just solve them. Solution of linear equations are very easy, and we can just solve that. So, therefore, only thing we will have to do is over here the thing that has to be supplied is the transition probability matrix. So, understanding the system, how do you construct this transition probability matrix, that will be your task. Okay. So, that is the only thing that you will have to do. Once you have done that, you are almost there, you can solve the associated these things. But remember, over here we still have not described anything that is Markovian. Okay. So, this without going into the description means Markovian was taken in the underlying process. We have not actually discussed about that. We have very carefully avoided that description, but actually that must be taken into account. This cannot be happening if the system is not Markovian, because then the whole system, the whole history has to be taken. Over here what we are doing, the next state where it will go. So, where the Markovian assumption was taken, we have written that particular matrix equation that pi n will be only dependent on the previous state and the transition probability. This is the Markovian assumption. That means it only depends on the previous state and it does not depend on anything beyond that. So, that was the associated Markovian assumption that we have already inherently taken over here. Okay. So, what we will try to do, we will try to see the implication of that one more time, and then from there we will try to build up the continuous time Markov chain in our next class. Okay. Thank you.